Miss Jody here with another video for Earth and Space Science. Hopefully things are going well and you're able to do some of our notes so that when we get back together we'll already have a lot of this work done during our separation. Now I know that I've reminded you in the past, but I just want to keep reminding everyone to do your notes on a half sheet of paper, and that way I can just glue them right in there underneath the label in your journal. So you have your notes done when we get back, and your diagrams, any diagrams that I send you like this, you can print those out and take the notes and do the coloring on it as we study together, and then those will already be done also. If you don't have a printer, I know some of you might not have a printer, and that's okay. I can print these off at the Science Center and glue them into your journals. They just won't be done, obviously, but if you do have a printer, then they can be nice and colorful and have all their stuff added to them. So either way, and then also don't forget, if you're one of the younger students, that I'm not expecting you to write all these notes, okay? So hopefully you watched that first video when I said, don't worry about this. This is a lot of notes. This is the Miss Jody notes. And so you don't have to write all these big words. What I'm doing is just showing you as we go along, and maybe just write one word or some of the drawings possibly that I would be showing you. And then that way you could have something for your note page, but it doesn't have to be anything like this. The big kids can do a lot of this because they're used to note taking, but even that, this is usually downsized when I get up onto the board. As you know, I try to make it more simple so we don't have too long notes. Okay, all right, so we finished up our chapter, which was chapter 10, and I'll just flip back through some of this so you can remember. Our last video, I had a little glitter going on, but starting with the considering the heavens, you remember that? And like the history of people being interested in seeing what was out there and above. For so many years, all we knew was the Earth, right? And that's as far as we could go. We couldn't escape velocity. We couldn't get up there. We didn't know what it was all out there, but we tried our best from our feet on the ground to observe what was up in the heavens. And so a lot of history with figuring those things out. And then we did a tour of our solar system. Do you remember that? Where we looked at all the different planets and things in our solar system just for a brief time. And then remember these wonderful little art pieces that you guys did before we got separated. And then we looked at the orbits and the elliptical orbits, and we continued on just understanding our solar system as a whole. And then after that, look, I'm missing pictures here. So sad that I don't get to see you. But I did get a few astronomy pictures before we left, so I'm gonna put those in there. Then we had a video on the asteroids, comets, and meteoroids, so we could understand what they were. And we had our little diagram, you remember, where we were learning about how this all works with the asteroids in the asteroid belt or in other places, and then understanding comets and understanding meteors and meteoroids and meteorites and all that. Then we went on to constellations, and so we were looking at the constellations, you remember that, and how that worked with our idea of what's called the celestial sphere, the big invisible sphere that we kind of keep track of everything from our feet on the ground looking up. And we had our diagram there, and then I also had you do a little craft on a constellation and study one of these particular ones. And then we, last video was on, I think this was the last video. I have to keep holding the book up. Maybe I'll put this astronomy book underneath here, because you know what? Our book is getting so bubbly because we have a lot of things that, look how big and full it is. I barely have any sheets left on mine. And yours looks like that too from all these years of studying the Earth and space science. We have so many things in there that are bubbly, like my little diver there when we studied the oceans. So it's getting pretty full, so it's kind of hard for you to see the edges here, so I might have to bubble it, move it up a little bit. All right, so we studied our sun and other stars and how that worked, and that's when I had a little glitter attack for missing you guys and doing crafts and glitters and all the fun stuff. So you can see I've got a lot of things going on here as my son is going through his process of fusion. And then we talked about the stellar groups and stellar explosions. So how stars can be grouped together, and then also how stars can explode in the stellar explosions. And remember, we had done this one, the popping of the canister tubes to create the supernova, and that would then leave behind a cloud of interstellar gas and dust that we called the nebula. I also added a little bit of glitter. Since I had the glitter out last week, I added a little bit of glitter just to make that dust in that nebula. So we finished that one, and then I also gave you an idea, if you wanted to and had some glitter, to do a fun little galaxy glitter. Mine turned out really good, but again, just glitter everywhere. So if you don't like to do glitter, that's fine too. You could just draw it out and be creative in that way. We talked about the different types of galaxies. Mine turned out really good with that really thin silver glitter. I like that one. All right, so we finished that up, and I'm saving some picture pages just in the hopes that we can get back together and I can get some pictures in there. I really would love to see you again, and I hope it doesn't go on forever. And I know most of the time people would really cringe at the idea of summer school. But if it goes on too long, I'm hoping we can at least get back together in May, but if it went on too long, could we get together just a couple times in June if we're allowed to get back together? So we could do some experiments and have some fun. We'd already have our notes done. So hopefully May, that's my goal, and that's what I'm hoping for. But if not, maybe June, if they let us get back together for a little bit, maybe your parents will allow that. All right, so our next topic is moving into chapter 11, where we're going to look at the instruments of astronomy and how we've discovered these things. So our title page for this notes is Instruments of Astronomy. Okay, and don't forget, just write that. Oops, knocked my little thing out of here. Just write that on the back of your note page so we can keep track of which ones go where. Okay, if you remember that. All right, so the first one, looking at the instruments of astronomy, we're going to look at the instruments that are what we use that's in the area of what we call visible light astronomy. So that'll be the study of astronomy using a variety of optical telescopes that work with visible light. So what that's saying is telescopes originally were created to utilize this visible light to see things from a distance, right? So we have ones seeing really things far away, the telescopes, and then we have the ones that are now also made to see things very small, the microscopes. And so these tools have been used to create these wonderful ways of us seeing things. So with the visible light astronomy, what that is a telescope that works with visible light. So what we have to do is we have to remember what visible light is. And on the diagram that I sent you, this should be kind of easy because we've studied this before. The idea of light as a whole, now light's a very complicated topic, and you can't just say a few words on light. You really have to study light for a while to get a feel of its complex nature. It's really very dual in its nature, so it's got wave-like properties, but it also acts like particles, and it's just amazing. Light is something you want to spend a whole year studying, which I would do that, but no regular person wants to do that with me, I would guess. Now, when it comes to light, I'm going to just use my highlighter to represent all light. So light can be represented in many different forms. And so as I'm drawing my little highlighter here, I'm going over across these what we would call waves. So as I start over here, I have very, very long, big waves, right? Longer wavelength, the length of the wave. And then as I get farther down, I kind of get to this little middle area, and then I continue, and they keep getting smaller. The wavelengths, the length of the wave, gets smaller and smaller and smaller and smaller and smaller and smaller and smaller. That's because light can manifest itself in so many different ways that all of these waves the long ones, the medium ones, the short ones, they're all considered light. They're just different categories, because here's the problem. There's only one little area, which is this little spot on the chart, that's actually visible to our eyes. Now what they've done in this diagram is they've blown it up here, because it's so small. How could you list it right there? But it's really just this small amount of wavelength that we can see, this small little category of wavelengths, frequencies that we can see. And so they put it up here so you could separate it. So what happens is this little area, which is visible light, is really a combination of all the light, which we normally see in color. So you know the prism experiment. We're going to look at that on the next note page, but just as an introduction. So what we have is that our light in this visible spectrum, this little area that's visible to our eye, is where we would see colors like red, orange, right? Yellow, green. I don't even have to do yellow, do I? Because it's pretty much already yellow. I made it a little yellow, and then green. And then, of course, I'm not doing this really super correct on where this is at on the diagram, because it's black and white, and I don't know exactly what colors they got going on here. I probably didn't do it very correctly. I'd have to look at the wavelengths there to know for sure, but you get the picture. So this little spread out version, I got two markers that didn't work. So you got to remember the rule of our markers. They go in the trash if they're all dried out. That way I can remember and figure out which ones are the good ones and which ones aren't. All right, so this little spread out is just this little version of that, which we call the visible light. Now with the visible light spectra, that's what we can see. And so many of these telescopes are built on the area we can see. Now later on, we found out that there was all these other sides of light, the ones we could not see, and we could also use those and create new kinds of telescopes. But at the time, what we really understood was the visible light, the colors that we were used to. So in the visible light astronomy, it's the idea of taking that visible light and using it to try to see things and figure it out. And so what they did is they started creating these telescopes. Now the two main types of telescopes here that we are looking at is the refracting telescope and the reflecting telescope. Okay, so the refracting telescope, and see how bubbly this is? I still can't even get it. Here, let me see if I can put a book underneath this side of it. There we go. Is that a little better there? So you can see, since it's my book's so big and bubbly. Okay, so refracting telescope. What that one is it uses lenses to gather light and then to form an image. And this is done through the process of refraction. Now, refraction, if you've ever studied light or any waves, refraction is the process of bending it, refracting it. And so with these particular telescopes, they're going to bend the light. So let's say, for instance, and I'll just draw it over here as a visual, and then I'll show you what it looks like in the telescope. So say light was coming in, I can use a device, and a lot of times we see this refraction even when light is hitting water or something in a glass. Doesn't matter what it is, different substances will bend it differently. And so say I have something that it can go through. Instead of it staying straight, it might bend the light maybe this direction. Okay, and so it's a tool to bend the light to where we want it to be. So bending it. Now, with the bending process, I'm going to show you what that looks like in the telescope form. With the bending process, that's one way of using the light to see what we need to see. But what about the process of reflecting the light? And so that's kind of like what you see with mirrors. So let me draw this is going to be my mirror, where this one was a lens. This was light going through and it being bent. And then this one, I'm going to have my little mirror. And as light is coming at it, a reflection is, instead of it going through it and bending it, it's going to reflect off of it. Okay, and so let me do those a little darker with the highlighter's kind of bright, but so we can see the rays. So as the light's coming in straight, and then it's getting bent a different way. Okay, but with this reflecting, it's coming in and hitting a certain point. These are the rays of incident, and they're hitting that, and then they bounce off, and this will be the rays of reflection. and you can use that to take a look at things you want to look at. And so these two ways of experiencing light can be used to create the telescopes that we want to take a look at what's out there through. Okay, so the telescopes, let me show you what that would look like. Now I can take this off there because this one's a little flatter here. So back on our diagram, this particular first lens, which is your typical one, when you draw a telescope, usually this is what you draw, and you put a little tripod there, and you're looking down here and looking up at the stars. And so this is what we would normally think of a traditional telescope. So with the traditional telescope, we got the light coming in. So this top part, okay, so I got all this starlight coming that we're trying to figure out. Okay, and so at the top here is this lens is what we call the objective. So what the job of this lens is to collect as much light and bring it in down through the tube. And as it collects as much light as possible, then it's going to eventually come down. Of course, there's going to be a change as it comes down. This lens will bend it, right? And so that's that process we call refracting. So it's coming in straight, it's bending it, and this light is being bent, and then it'll eventually come to a point together where there are different parts of the lens, as it's bulgy, will refract the light in different ways, and it will join here at this point. And then we see this crisscrossing here, and then at the end we have this second lens. Now the second lens is called the eyepiece, and it's magnifying lens that enlarges the inverted image. So that's why when you see the images upside down, when you've studied that before, that's what's happened here with the bending of the light and changing that in the refraction process. And then this little eyepiece is helping you magnify that little picture. And with this particular model, it's focused by adjusting the distance between the lenses. So if we want it to focus more, we have to worry about how far apart these lenses are. So sometimes this is why you see really long when they're the refractor type telescopes. They're really long and skinny tubes because they're making them longer for more of that focus point. Now, the largest, at the time that our book was written, they had noted that the largest of the refractor type telescopes had a 40-inch diameter objective. So the objective, which is its objective is to bring in the light, so that can help you remember, all the way down to your eyepiece, was 40 inches in diameter. Now, one thing to note on both of these telescopes, this is why I've got two little arrows here, the wider the objective, the brighter the image and more detailed. So they've learned over time that we want to have the wider side of things with this one and this style of telescope to get that brighter and crisper detail. All right, so that's the first one where we're bending light. And then the second one, instead of bending it and refracting it, we're going to reflect it. So it's gonna fuzz right off of the mirror here. So in comes the light nice and straight like light does, and then it hits the mirror down here. So the mirror, it's a curved mirror. You can kind of see that in your diagram. And that's what's in place of the objective lens. So here you'd have a lens. On this one, you're gonna have a mirror, which makes sense because you don't want the light to go through it. You want the light to bounce off of it and reflect. And so you have this mirror, and this mirror will make it bounce off in a certain angle because of the curvature of the mirror, and it will bounce off to a certain spot where there's another mirror, which is this mirror would be called your primary mirror or the objective mirror. Some people call it so they can remember it's the gathering of the light. So the objective is always to gather the light here. This objective is gathering it, but in a sense, it's gathering and bouncing it up. And then there's the second mirror, the secondary mirror, a little small flat mirror, so that when the light comes up, and you can see it, it will go up and bounce off, and then it will, through the mirror, it'll be reflected again to the eyepiece. And same with this little line of light. It will bounce off the secondary mirror and into the eyepiece. And so this bouncing off reflection will allow us, now you notice that your eyepiece is not down here, it's up here because it's gathering and bouncing it up to the mirror and then to your eye. And so this is still called the eyepiece. like this one is. And then, of course, this is still called the objective, but it would just be the primary mirror objective. And then we've got that little small secondary mirror. Now, do know that these are just simple versions of both of these. Even in this one, as you can see, I noted, you could have more complicated versions with more lenses for this one. This is just a stripped down, simple one. But you can even make this more complicated, and you can make this more complicated, in a sense, with your distance and your size and all that. And they have special like cameras that can be attached to things, and it can be really fancy, which is awesome. But just for us to visualize it, we want it to be simple. I guess I'm going to put all the starlight coming in here because more of those would be entering in. All right, so with this one, at the time of our book, it said the largest of the reflector mirrors, the big mirrors, were 33 feet. So that's a large mirror. Now, when we look at the telescopes like that are up in space now, like the Hubble telescope, it's this particular kind of the reflector type telescope. So both of these have a great contribution in astronomy, but it just depends on where you're at, what you're looking at, and of course price and all that too. Some prefer the reflector ones over the refraction lenses, but they can both be beneficial. All right, so as a review, visible light astronomy is when you're actually using light to see these things. You can bend the light with the refracting telescope like this, or you can reflect the light so that you can see the particular image. All right, now when we're using light astronomy, there's gonna always be obstacles. And as we know, when it comes to light, there's obstacles to seeing light. And so at certain angles, reflection, refraction, diffraction, there's all these things about how waves work in light. So there's some obstacles we have to overcome. Well, first of all, sometimes these things are too faint. They are so far. And so what they've learned is to make the telescopes larger, using them larger telescopes to create the images that they want to see from those too faint objects. Also using sensitive digital cameras instead of the eyepiece. So instead of your eye trying to do this analyzing of the data, if you've ever looked through a microscope, this is also very key in the microscopic world, because when I use my eyepieces for my microscope, sometimes my eyes are like, they hurt after a while. But the one that I have hooked up by the whiteboard, you know, the one I have my microscope hooked up to the computer, that one is so great because I can just sit there and stare at the computer screen as my camera that's hooked up to my microscope does a lot of that work for me. And I think in the same way, the digital cameras will help because they become the eyepiece and can have the images done digitally so you can see that. So you can make them larger, you can make them more sensitive with digital cameras. There's always going to be problems with the atmosphere. Now, it's something we have to remember. And when we study the atmosphere, we know that the Earth is covered by those 5 blankets, we called it, those layers of air that protect us from the incoming things, and then also with our warmth and all the things that we need for our survival. So, but the problem is when you have your feet on the ground and you're looking up to the stars, you're looking through those 5 layers. And even though they're invisible in our mind, the light that's coming in towards them or towards us has to go through those 5 layers. And so there's certain areas in those layers that distort the light, that bend the light and cause it to not look exactly like it should if we were looking directly at it, if we were outside of the 5 layers. So there's always going to be problems with the atmosphere. And so what they've learned to do is they've learned to use computer-controlled mirrors that constantly flex and bend to correct the distortion. So they have these mirrors hooked up to computers, and they can bend and reflect so that the distortion is taken out of the picture, because they can use physics to figure out what's happening with the distortion, and then they can correct it. So that's cool. Also, they were smart in learning to build the telescopes, the visible light telescopes, on mountains. So the higher you get up, the less of the layers of the air on you, so you can have less distortion. So that's smart, building those giant telescopes, making them real big and putting them on mountains. And then, of course, then there was some brilliant scientists that said, hey, what about the idea, why don't we get out of the blanket? Why don't we put a telescope above the blankets and see what we can see? Because then we wouldn't have all that distortion. And of course, that's the very thing they chose to do. In 1990, NASA and the European Space Agency, ESA, put up the wonderful, well-known Hubble Space Telescope. And that's when we got those images that we were just mesmerized by, because space was way more than what we could have imagined, now that we escaped velocity and got that telescope above the layers and used it to observe what was out there. And so with that, we review the idea of using visible light, this little tiny spectra here, right, little there, and using that with the reflector type telescopes the refractor type telescopes, the bending the light, see, it comes in the lens and bends it, or the reflection where it comes in, reflects off to another mirror and then into the eyepiece. Okay, so those are two great tools for observation. Now the next one is ways of us observing things in our astronomy, is the idea of using spectroscopy. Now I always have trouble saying that word. Hopefully I didn't do too bad there, but you'll hear me mumble over it. I don't know if it's the S's and the C's and too much of something, and I have pronunciation problems anyway. We all know that. All right, so spectroscopy, I'm actually doing well. And that is the study and measurement of spectra produced when matter interacts with or emits EM radiation, which is electromagnetic radiation. Now that's a big word, a big mouthful. So let me explain what's happening here in that spectroscopy thing. So on the second part of your diagram that I sent you, there is the top is the prism experiment. You've heard of this before, in the time with Sir Isaac Newton in the mid-1600s, when he started realizing that light, though it looked white, could be actually separated using a prism. If you shone the white light through, the prism would separate the light into colors. And so as the colors would come out on the other side, maybe shine against a wall or a piece of paper, you would see this division, that white light was really a combination of many colors. And so we've learned these beautiful colors. Everybody knows the colors that we call the colors of the rainbow. And what that is it's the spectra of visible light. So the ones that our eyes can see, not the part of the spectrum that our eyes can't see, which is the radio waves and the microwaves and the infrared rays and ultraviolet and X-ray and gamma, but just this little bit of the waves that we can see, the visible light. Now my blue, let me see if I got another blue. That blue had seen its day. I don't really have another beautiful blue, but I do have a crayon. And there we go. So when the prism separated the light, these colors appeared, and then at first they thought, oh no, that it was not necessarily coming from the white light, but then he took the colored light after going through the first prism and put the colored light back through another prism, and it turned back into white light. And so then we realized that this was the spectra. Now, the visible spectrum, sometimes we can remember it by the terminology Roy G. Biv, and that's red, orange, yellow, green, blue, indigo, and violet. Now, sometimes people don't put in indigo. They just do BV, which still sounds like Roy G. Biv, so it's fine. Some people put indigo in because back when he was first discovering it, there was this idea that there was 7 colors, 1, 2, 3, 4, 5, 6, 7, and then now some people say no, indigo and violet, they're of the same, and we don't really need to have that one there. So, however, but either way, it helps you remember this visible spectrum. So what happens is white light going through the prism it can be interacted with matter. Now, matter is anything that has mass, right? And takes up space. So it's going to be made of atoms and it's going to take up space. And so what they did is they would take these gases, and I don't really want to use a color because I'm talking about gases that you can't see, but I'm going to have to do something to illustrate it. So let me see. How about I use a gray? And you hear the picnic table squeaking? In case you missed those squeaky picnic tables in the upstairs lab, there's your little treat here of my table squeaking. All right, so here's my prism. So as my white light is coming in, okay, picture I have this big bubble of gas in front of it, okay? So say I put this bubble of gas. Now remember, gas would be invisible, but I'm drawing these little dots to represent that the gas is made of atoms, so it has mass, and it takes up space. And so taking the white light and shining it through the gas. So whenever we shine it through the gas, we're able to see that there is a spectrum that comes out of that, shining through the gas. So if I don't have the gas there, I get what's called the continuous spectrum, which is the Roy G. Biv. And that's separating pure white light through a prism to all its colors. And so when you look at this little spectrum here, this is what we would call a spectrogram. It's a picture of how light is coming through. And so when we would shine the light regularly just through the prism, it would just be a continuous spectrum, just this beautiful. And this would be, which you can't see, but when you pull it up on your computer, you'll see it's colored, and it will have all the colors to it. It'll be the very same colors that we see with Roy G. Biv, and of course flipped. And so when we see this particular colors on the spectrum, they kind of all blend together, but you would definitely see red, orange, yellow, green, blue, indigo, if you want to put that one in there, and violet. But when you put a gas in front of that light, like let's say the gas of sodium or hydrogen or calcium or mercury or whatever, you would put that in front of the prism and allow the light to go through the gas and then through the prism, and the lights would come out. Now, why that's important is because when it would do that, some of these atoms, depending on which gas they are, they will absorb certain amounts of the light. So white light through a gas, certain colors are absorbed. And this is special to each one of the atoms, like hydrogen or any of them, like calcium. When you put the light through them and then through the prism, it will not come out with every single color. It won't be a continuous spectrum. It'll have some areas where there's just black lines. Those black lines represent the fact that those particular colors were absorbed. And we call those dark lines absorption lines. So when you look at this, it's going to be hard to visualize this because I have it on black and white here. But when you pull it up on your computer, not that you have to print it out in color, because I don't want you to be wasting ink. And actually, I'll show you the picture in our book because it has a better coloring there for us. But you see, here's continuous spectrum. So that's all the colors together, all blended together. But when the light is going through a particular gas, there's this light source, gas partially absorbs some of the light. So then when it comes through the prism, only some is showing. And there will be these little black lines. These little black lines show us the areas of light that's absorbed. Now, why that's important is because each element will have its own spectrum lines, its own absorption lines. So hydrogen will always look like this when you put it through the prism, or you shine the light through hydrogen and then through the prism. And calcium will always look like this. It's like a barcode. It's pretty fascinating because it's like the key to that element. Like we've solved the idea of each element has specific lines of where it's blacked out, and that's kind of its pattern. So just like when you go to the grocery store and you have the barcode, this is the barcode of calcium, this is the barcode of mercury, and this is how they do it. Now, what's interesting is because we can do that with our telescopes to actually look at things that are very far away, and they can give us, I'm popping this up again here to make it a little better for us, they can give us some insight into what certain stars are made of, certain obstacles in space that we're looking at. just by doing that same thing, shining that light and using the spectra that's produced to be able to view what's really there. So we use that device. It's called a spectroscope. Now, it's a device that splits light into a spectrum for analysis. So it makes the lines for us, and we can analyze the lines and go, oh, okay, it looks like this element is present a lot in this star, and it looks like this element is present in this star because of those little barcodes that the light makes for us. Now, when you take the picture, like I was showing you with the barcodes, it's called a spectrogram, an image that records the spectrum produced as it goes through the gas and then goes through the prism. And so we have a lot of data from doing that in the labs, shining the light through different gases. Then we know the codes of the different elements, and then we can use the light coming from space to also code and figure out what's out there and what elements are part of each one of the things that we're studying. Now, also with spectroscopy, okay, we have radio wave astronomy. Now, radio wave is the study of space objects at radio frequencies. Now, if you remember in this last diagram, I'll flip back to it, when I was telling you that this is the visualization of light as a whole, and that we see this little visible spectrum, but there's all these other waves of light that we can't see with our own eyes. We need special tools to detect it. One of those light sources is radio, what we call radio waves. Now, it's weird when you hear radio because you think to yourself, wait, radio waves, that's sound. That's because we use these waves, these particular light waves, to transmit our radio sounds, the things that come through our radio. But it's really these light waves that we have named radio waves, okay? So these long light waves, what's great is we can use those long light waves because they can sense things really far, and we can use those in our study of space. So if you look at this right here, in the radio wave astronomy, we have radio telescopes. Now, the radio telescopes, they have a big, large disc that reflects radio waves at an antenna. So if you think about it, and I'm going to show you the diagram, you think about it just like the telescopes we just learned about. It's going to be very similar, but instead of using visible light, it's going to use the radio wave light that's on the beginning of the spectrum. So here's the little dish. What's the dish doing? Well, the dish is functioning as the objective. So what did the objective do? Its objective is to bring in as much light. So as light is coming here, and now we have to visualize that this is not visible light. We cannot see with our eyes, but I'm still going to bring it in, okay? And so as I'm bringing it in, it's this special wavelength of light that we can sense from out in space, and it comes in, and then this is going to act just like the reflective telescope. It's going to reflect it up to the antenna, and then the antenna is going to serve as the camera. So the antenna is like the eyepiece in a sense. It's going to sense the radio waves, and so that they can be analyzed and we can figure out what's going on out there and what these radio waves can tell us. Now, radio waves are neat because they have these long wavelengths, and they can penetrate interstellar gas and dust. So remember the nebula or the nebulae, if we have plural. Remember that when it's that dust and gas that left over from the supernova? The radio waves could actually penetrate into that gas and dust and measure it for us so we can get a picture of it. Now, it's not the picture like what you're used to seeing from Hubble and all that, but it's a picture of the radio wave activity. And then they can use their computers to illustrate what that would look like in space. And so then with the radio wave world, we looked at the history, okay? And so with the radio telescope. So the history, in 1930, there's a gentleman named Carl Jansky. I'm trying to flatten this out here for you. Jansky, and he was a telephone engineer. And so what he did was work with telephones. So back in the day, the telephones were linked and they had cords. You guys weren't alive to know such a thing, but we didn't have everything wireless back then. And so they were all corded up, but a lot of times you'd be on a phone and it would be staticky. Now, I'm not saying I was alive in 1930. Don't any of you gooseballs run with that one next time. But I mean like back in the day when there was telephones, okay, that were hooked to the wall. All right, so this particular guy as a telephone engineer, he was figuring out like some of the things that were involved with the static that was coming from like the telephones, and he realized that there were actually static coming from radio waves from space. And so they were kind of shocked by that. Well, wait, okay. So some things in space actually emit radio waves. They actually emit the waves, and then the waves eventually can get to us, and we can use those for our analysis of space. Now, with that, there's the world of interferometry, which is, think of the word interference in a sense. Interference is when we have waves that are going to come together. Now, sometimes that interference is destructive, which means they come together and they mess up the waves. But sometimes interference can be constructive. It can be good because it can kind of amplify our understanding of the wave. And so when it comes to interferometry, just think of that word interference, because what it's doing is analyzing radio waves detected by different radio telescopes that are far apart. So instead of just using one, we use more than one, and they're separated very far. In fact, they have a kind of a detailed plan where the different radio waves are in different countries, and they can kind of all work together. And then they use that data and analyze it together to get a better visual of the radio waves and what's out there. So helping each other. Now, our book talks about how Sagittarius A, which is the probable black hole, probably what's at the center of the galaxy, that it actually emits powerful radio waves. And so they can do a lot of discoveries with the radio telescopes when it's something in space that's emitting a ton of radio waves, very powerful waves, and we can read those with our radio telescopes. So there's a lot that we've already discovered, and there's a lot to be discovered using the light astronomy, spectroscopy, and the radio wave astronomy. And so we have really seen amazing things in our space world. And then, of course, like I said, with the reflector telescope like the Hubble, and then the James Webb, we've been looking at the James Webb for quite some time now, and in our space exploration camps, and anytime I teach on astronomy. And there's been some delay with the James Webb, but it is the telescope to replace Hubble that is going to be way more complex than even Hubble. So I can't wait to see even more than what we've seen in our discoveries this far.